In this video, we are continuing section 5.3 on log functions, and we're going to go over how do we graph log functions. Okay, so I want to get right into an example. I want to sketch f of x equals log base 2 of x, and then do all of our usual stuff like domain, range, intercepts. There's going to be a balance point on log function graphs, just like exponentials, and the asymptote equation. Okay, all right, so to get the graph, I'm going to plot some points like we did with exponentials. So I'm going to plug in some x values and then keep track of, well, what's log base 2 of x going to equal? Okay. I just need to be a little bit careful about what I plug in. I need to be a little bit careful about what I plug in because for me to be able to evaluate log base 2 of a number, like let me try a number like 4. I need this number that I'm inputting to be a nice power of 2. So for example, if I was plugging 4 into log base 2, I would get log base 2 of 4. And let's say I don't know what that is. Let's say this is some mystery number. Well, when I convert this to exponential form, this is asking, well, 2 to what power? 2 to what power equals 4? And I can see what that's going to be. I can see it's going to be a squared. I can see that the number that goes in here is 2. So that is what log base 2 of 4 is. It's going to be 2. And I'll write that here in my table. Okay. But it was important for this to work that the number that I had on this right-hand side was a perfect power of 2. So this input in my log function needed to be a perfect power of 2 for this to be like an easy computation. Okay, so what are some other perfect powers of 2 that I can plug in? Well, 2 is. 2 is a perfect power of 2. Also 1. And let me do some things that will involve negative exponents, like 1/2 and 1/4. And just to see what happens with some other values, let me also just do 0 and -1. Those will be helpful to explore. All right, so what are the outputs I get for these? So first, if I plug in 2 into log base 2 of x, the question I would be asking myself is, well, 2 to what power? So the base 2 that I'm writing is coming from the base of the log. Well, 2 to what power equals 2. So this 2 that I'm writing right now is the output. Ooh, let me put that in a lighter color. This 2 that I'm writing is the output. Well, that's matching up with the number I'm plugging in for x. So what would the exponent need to be? Well, it would have to be 1. Okay, so that's log base 2 of 2. It is just 1. All right, so if I keep going like this, now when I plug in 1, I want to know 2 to what power equals 1. Okay, and that power is going to be 0. That's what log base 2 of 1 is. It's 0. Okay, next one. Next one, I want to know 2 to what power equals 1/2. And there the exponent's got to be -1. So -1. For the next one, let me try not even writing this thing. Maybe we can just do it more quickly. I want to know 2 to what power equals 1/4. That exponent is going to be -2. Nice. All right. So what about with these remaining 2? So what about with 0, if I plug in 0, I want to know 2 to what power equals 0. And if I plug in -1, I want to know 2 to what power equals -1. Well, both of these, nothing works. Nothing works. Nothing works because 2 to any power is always going to be greater than 0. It's always going to be positive. So there's no way it's going to equal 0. There's no way it's going to equal -1. So as a result, both of these are just going to be undefined. Okay, so this is one of the key properties of log functions. We cannot take log of 0, and we cannot take log of a negative value. Okay, so let's take the points that we do have and start to plot them in our graph. Okay, so I know that when x is 4, the output is 2, the y value is 2. When x is 2, y is 1. When x is 1, the y value is 0. And when x is 1/2, the y value is -1. When x is 1/4, the y value is -2. Okay, So now if I connect these points, it's starting to make a graph that looks like this, and then over here it's going to really snuggle up next to that y-axis. Okay. So before I write all of this stuff, domain and range and whatnot, there's a couple of observations I want to make about the graph. So one is, I know that log functions are inverses of exponentials. And I know how the graphs of inverses are related. So if I draw the graph of the diagonal line, y equals x, so this is just y equals x, well, inverses are supposed to be reflections of each other across that line. So if I draw the reflection of my log base 2 graph, so this is y equals log base 2 of x, well, the reflection of that across that line, I'm going to put it in a different color, well, that'll go here and here. I'm just drawing the mirror images of all my points. The mirror images of all my points across that line. And if I connect these, we are getting our exponential function graph. So the inverse of log base 2 of x, well, that is y equals 2 to the x. And that matches the graph of y equals 2 to the x, what we know it to be. So that's good. So just like the exponential function has a balance point at 0, 1, a log function will have a balance point. That's the mirror image of that across y equals x. So that's at 1, 0. That is the balance point. That is the balance point of a log function. Okay, so I'm going to label that here. My balance point is at 1, 0. That's kind of where the graph changes from growing very quickly on the left of the balance point to very slowly on the right of the balance point. All right, let's write all this remaining stuff. Domain. My x values, well, they get really close to 0, but they never reach 0, so parentheses, and then onwards to infinity. My range, my y values, well, they can be as low as I want. They go downwards to negative infinity. But they can also be as high as we want. This graph keeps on getting higher and higher and higher forever, so onwards to infinity. So one thing to notice about this domain and range is, notice that they're kind of like the reverse of what the domain and the range are for y equals 2 to the x. And that's what we'd expect because they're inverse functions. They're going to swap the roles of the domain and the range. X-intercept is at 1, 0. Y-intercept, well, there is none. This never touches the y-axis. And whoops, oh, this is copy-pasted. This should not say horizontal asymptote because this has a vertical asymptote. And the vertical asymptote is just on this y-axis. Vertical asymptote is on that y-axis. So that equation is x equals 0. So there's a vertical asymptote at x equals 0. And that's our graph of log base 2 of x. Okay, so let's graph some other log functions and see how they compare to this one. Okay, so I want to graph now log base 2 of x as well as log base 3 of x on the same set of axes. So let me start by drawing log base 2 of x just because I already had that graph. So log base 2 of x, if I look at my picture above, I know when x is 1, the output is 0. When x is 2, y is 1. When x is 4, y is 2. And then when x is a half, y is negative 1. When x is a quarter, y is negative 2. And connecting these, my log base 2 of x graph looks something like this. So that's my graph of y equals log base 2 of x. So now let's get the graph of y equals log base 3 of x. So I'll plot some points to help me. So I'll get some x values, and then I'll keep track of what output I get. So just like with log base 2, I plugged in some perfect powers of 2. For log base 3, it's going to help to plug in some perfect powers of 3. So I'll do just a couple of numbers. I'll do 3, I'll do 1, and I'll do 1/3. Those are all perfect powers of 3. If I plug 3 in, I would want to know, well, let me put it in gray. Well, 3 to what power? So the 3 that I'm writing, that's the base of that log. That's going to be the base of the power, equals the 3 that I have over here. Okay, and that exponent's got to be 1. Okay, so log base 3 of 3 is 1. If I do the same thing with 1, let's do this more quickly. 3 to what power equals 1? Oh, and that's 0. Last one. If I plug in 1/3, well, that exponent is going to be -1. Okay, so let's plot these points. Let's plot these points. All right, so for this graph, well, when x is 1, y is 0. So it's got the same x-intercept, the same balance point. When x is 3, the y value is 1. Okay, and when x is 1/3, the y value is -1. Oh, so that's like somewhere here, 1/3. When x is 1/3, y is -1. So if I connect these, well, on this side of the balance point, it's kind of going below the graph of log base 2 of x. And then on the other side of the balance point, it is above. It is above the graph of y equals log base 2 of x. So that's my graph of y equals log base 3 of x, and how it compares to log base 2 of x. Okay, awesome. All right, so I want to do one more of these. Part B, what if I now want to graph log base 2 of x and log base 1/2 of x? So log base 2 of x, we've done that a couple of times. Let's just plot those points. So when x is 1, y is 0. When x is 2, y is 1. When x is 4, y is 2. When x is 1/2, y is -1. When x is 1/4, y is -2. And connecting these, we got our graph. We got our graph of y equals log base 2 of x. Okay, and let's plot some points to get the graph of log base 1/2 of x. So I need to plug in some perfect powers of 1/2 because my base is 1/2. But powers of 1/2 are also powers of 2. So I get to plug in numbers like 2 and 1 and 1/2. Those are all powers of 2, and they're all powers of 1/2. Okay, so what happens when I plug these numbers in? So if I plug in 2, I'd want to know, well, 1/2 to what power equals 2? Well, that exponent would have to be a -1. -1 to reciprocal the 1/2 and make it become a 2. Ooh, so that's -1. If I plug in 1, well, then I want to know 1/2 to what power equals 1. But to get 1 out, I need the exponent to be 0. The exponent's got to be 0. And the last one, let's practice doing it without writing it out explicitly. I want to know 1/2 to what power equals 1/2, and that's just 1. Okay, so let's plot these points. Let us plot these points. So pick a new color. Okay, so when x is 2, the y value is -1. When x is 1, the y value is 0. Okay, and then when x is 1/2, the y value is 1. Ooh, okay, so if I connect these, it turns out the graph is going to look like this. It's going to look like this. I'm plotting another point there. It's looking like this. This is the graph of y equals log base 1/2 of x. It's a reflection of the graph of log base 2 of x, but across the x-axis. Okay, so when this base is something between, when it's something between 0 and 1, then our log graph will be like this. It'll be going downwards. It'll be decreasing. All right. Okay, so let's do one more graph sketching example. Okay, so let's sketch the graph of absolute value of ln of x. So absolute value of ln of x. All right. So to get it started, let's see if we can draw the graph of y equals ln of x. So the graph of y equals ln of x. Let me draw some axes. Okay, so one of the key things to know about this one is, well, ln is just another log. Like ln means log base e of x. So I would kind of expect its graph to look like the graphs of log base 2 of x and log base 3 of x, especially because, well, e as a number is between 2 and 3. Remember, e is about it's about 2.7. So I'd expect it to kind of look like those graphs. Okay. In fact, if I plot some points to help me here, I'll just plot a couple of points. So I'll keep track of x and ln of x. I'm going to plot 1. Okay, if I plug in 1 and I get ln of e, well, the question I would be asking myself is, the base of the log is an e. E to what power equals, oh, oops, sorry. sorry, I made a mistake. So it's not ln of e. I'm not plugging in e here. I'm plugging in 1. I'm plugging in 1, right? So, but the base of the log is e. So I want to know e to what power equals 1. Okay, so that exponent's got to be 0. So that means ln of 1 is 0. Let's plot that point. So when x is 1, that's a point on the graph at 1, comma 0. It's got the same balance point that those other log graphs have at 1, comma 0. Okay, well, what's another nice number I could plug in? Well, because the base of this log is e, I need to plug in perfect powers of e. So e works. If I plug in e, well, I would want to know e to what power equals e. Oh, but that exponent's got to be 1. So if I plug e in, the output is 1. Okay, so when x is e, the y value's got to be 1. So that would be here on the graph. And if I start to connect these, my graph of ln of x is looking like this, really similar to the graphs of log base 2 of x and log base 3 of x. Just, it turns out it's kind of in between those two. It's in between those two because e is in between 2 and 3. Okay. So if I got that graph, what would taking the absolute value of the whole thing do to it? So let me draw some x. Ooh, not liking that. Let me draw an axis. Okay, so what I want to do is I want to first give you about 30 seconds to try this on your own. So 4, 3, 2, 1. Pause the video and see if you can draw, see if you can remember. Well, how does taking an absolute value of a function affect the graph? All right, so hopefully you did that. Hopefully you paused it and tried it. Let's talk about it. So when I do take an absolute value of a whole function, remember that what we do is we erase the y values that are below the x-axis. So we erase those negative y values, and we make them positive. So any y values like these that are below the x-axis, those negative y values, the absolute value is going to make them positive. So we're going to erase them and then reflect them across the x-axis to make them positive. So any part of the graph that's already above it, that's already got positive y values, well, that stays the same. So when x is 1 at that balance point, onwards this way, all of that's the same. So I still got this point at e comma 1. But then the part that was below the x-axis, all of this, that gets reflected up. So when that gets reflected up, that's going to look like and it's going to snuggle up next to my y-axis going this way. Okay, so that is my graph of absolute value of ln of x. And then it says to get the relevant points. So let's do that. Okay, so let's do intercepts, x-intercept, y-intercept, and log functions. There's going to be a balance point. Balance point. So let's start with the balance point. The balance point did not move going from the first step to the second step. So the balance point is still at 1 comma 0. And that is also the x-intercept, 1 comma 0. And y-intercept, well, looking at the picture, there is none. There is no y-intercept. Alrighty, so that is our graph. So in the next video, we'll go over how do we find domain of log functions.